Okay, hello again, everybody. This is Statistics for Linguists. This is our last lecture of the semester on linear mixed effects models. We're just continuing on for the second part of the tutorial from Bodo Winter that we started in the previous lecture. And if you want to follow along yourself, actually maybe I'll do this just to kind of be on the safe side, but you can open up this PDF, which is located on Professor Winter's website. And there we go. Okay, so this is a tutorial for performing linear mixed effects analyses in R. And we've kind of went over the basics of the concept of how they work in the previous lecture, but we're going to learn a little bit more in detail, kind of the machinery behind the scenes in this lecture as well. So, right, we were dealing with the fact at the end of the last lecture that we might have multiple measures from the same subject, and that violates the independence assumption of a technique like ANOVA. And so what we're going to do to try to fix that is to add a random effect for each subject in our model. So what that means is we're basically going to assume a different mean value for each subject. And you can kind of think about it going back a little bit to what we did in the previous lecture. If you remember, when we were just trying to figure out if F0 depends on the sex of the speaker, we wind up with sort of a default intercept, at least the way R runs the model. F female is before male in the alphabet, so the default or the intercept value is going to be the average female F0, but that's just kind of across the board for any female speaker, and then there's an adjustment you make to that to get to the sort of the male average. But here we're going to say, well, there's like an average for every individual speaker. We're going to get more specific than just like, is that speaker a man or a woman? We're going to say, is that speaker Bobby or Susie, right? And so Bobby's going to have his own F0 sort of default, and Susie's going to have her own F0 default. We can't just assume that they're the same or that they might be like other speakers of the same gender. So we're going to, in other words, we're assuming there's a significant subject effect on F0 in our model, and we're going to suck up some of its effect on variance by positing random intercepts for each subject. Or maybe you can just think of these as like subject-specific intercepts. Might be another way to do it. So each random intercept is the mean value for each subject, more or less, when you take these other factors into account that we're trying to incorporate into our model. Excuse me, I have a cold today, so it's a good thing we're still online. But anyways, it's a little bit also like when we were doing first learning how normalization works and how to calculate z-scores. We learned the Lobanov method of normalizing vowel formant frequencies. And remember, you come up with a specific kind of formula for each individual subject based on their mean F1 and the standard deviation of their F1 and their mean F2 and the standard deviation of their F2. It's a little bit like that. So, and also in the previous example, we had we were looking not at just raw height measures, but we normalized them to a certain extent by looking at how the height of an individual speaker deviates from the mean height of speakers in our little data set. We're kind of doing something similar like that for F0, but we're just kind of normalizing it on a speaker by speaker basis, as it were. And so this is how we get what is called a mixed effects model. So we're modeling the randomness, at least by speaker. So that's going to be a different sort of variable than what we get from what are called fixed or systematic effects of these other factors we've been playing around with, like the speaker sex and their height, that sort of thing. And then, so those are fixed effects, and these are random effects for individual subjects. So a mixed model is basically those two things put together. That's what it means for a model to be mixed. You already know what the linear part of it is, but the mixed effects are fixed effects plus random effects. And then it turns out there's still going to be some randomness left over on top of that. Also kind of going back to the previous lecture, way back at the beginning, we kind of had this very simple model of pitch depends on the speaker sex and the randomness here at the end. And I said this is sort of a bit like, looking at the signal and the noise in our data. And I said we're going to dig a little bit deeper into the noise to try to get a little more signal out of it or a little more structure. And that's what we're doing here with this random effect of individual subjects. So we're trying to get a little more sense of where these measures are coming from by assuming that each individual subject will kind of do their own thing. And since we have repeated measures from those individual subjects, we can sort of normalize to a certain extent, how much each individual observation deviates from like the the mean for an individual subject. But there's still going to be some randomness left over. There always is on top of that. So there's some noise, but now we kind of have more structure in the signal part of our data. So here's the notation that the tutorial uses to create this sort of model or represent this sort of model. And this notation is being used because it's basically the notation that R uses. But here's our dependent measure, F0, fundamental frequency or pitch. And then that depends on the speaker's height, the speaker's sex, who the speaker is, and then there's like some randomness left over, which we're just calling epsilon, some individual variation for every single individual data point. Yeah, so the notation here is pretty clear for these independent factors, but then when you add the random effect of subject, it's in parentheses and there's a 1, and then one of these vertical lines like we saw in conditional probability. So it's one conditional probability line subject. That just says create random intercepts for every individual subject. Yeah, and that's what it's going to look like when we start doing this in R as well. Okay, so, right, we talked about those points, but there's a quote from the tutorial. What this is saying is, assume an intercept that's different for each subject, and 1 stands for the intercept here. So I don't know if we looked at an example like that, but you could just create like an intercept-only model. We'll see these eventually, but I'll show it to you ahead of time. You could, like, the most basic or null model, I think we've seen this somewhere down the line, is just to create like F0 depends on 1. And then I guess, you know, there would be like epsilon in there as well, but that would be a null model in R to just put that 1 there. Like we saw that, I think when we were building up the stepwise multiple regression models. So that's kind of the same one here, which is just saying 1 stands for the intercept. So at least give the model an intercept, and maybe there's nothing else that you can use in there to predict. At least that's the assumption you make in the null model, but this sort of model says at least check these factors, and we'll see if they're, you know, significantly different from that null model. Anyways, that's just about the notation. Here's more about the conceptual part of it. So you can think of this formula as telling your model that it should expect there's going to be multiple responses per subject, and these responses will depend on each subject's baseline level. Okay, right, like I said, we're kind of normalizing by subject in this respect. So this effectively resolves the non-independence that stems from having multiple responses by the same subject, right? And yeah, it's a little bit like the repeated measures, as I mentioned before, the repeated measures ANOVA, but we're getting more detailed because we're able to do this on a subject by subject or speaker by speaker basis, right? So that's pretty cool. And like I said, it helps to have more computing power to throw at this problem. And that's why these models have become more popular in recent years, just because they become a lot easier to use. Right, so this tutorial also talks about the possibility of by item variation. In our data set, that would translate to the possible structure and variation we would get out of repeated measures of the same words. So each word might have its own small effect on F0 for whatever reason. You know, maybe it's due to frequency or something like that, or maybe it's due to some particular combination of segments in the word or whatever. Maybe you just happen to say a word differently than the others. So strictly speaking, to give you an example, the measure of F0 we get from Summer's production of Peel is not entirely independent of the measure of F0 we get from Charles's production of Peel, and so on and so forth. Like, these are different subjects. We're already kind of taking that into consideration, but Peel itself, actually, you know, this is more about the subjects than it is about the words. Yeah. Yeah, so this is not entirely independent, but yeah, sorry, that's the point I wanted to make. So the independence there, the lack of independence comes from the fact that we're repeating the words over 2 different subjects, right? So there might be something special about the word peel, which, you know, we have to factor into what we can expect its F0 to be. Sorry about that. I get confused about this often myself. And so for that reason, we should also add a random effect of item or word into our model of F0. Yeah, so right, and this is typically the way you see these models get constructed in linguistics research, is that you have random effects for both subjects and items, as they're called. So subjects and words, if you're having people produce individual words or, you know, sentences or whatever individual trial you're recording data from in your experiment. So you have those 2 as random effects, and then you have whatever else you're interested in as a fixed effect over here. But this is the notation you use, again, for the random effects. All right, so let's make this work. So to be able to generate mixed effects models in R, we need to first install the LME4 package into our current R session. I mentioned last time there's like a package called ggplot in R, which is super useful and amazing actually. I said you can check it out on your own time if you want to. I'm glad we're doing this at this point because I'll show you briefly how you install a package in R. It's actually quite simple. So R is, a software package in its own right. And it has a lot of functionality, but you can add to it. There's just a lot of stuff out there that people have worked on and contributed to the project, which doesn't come automatically installed with R. So to install it, in this particular case, you just use this command, hit return, and then it shows you, well, you got to download this software, this new package of software from somewhere out there in the world. We could go anywhere we want to, almost. I'm just going to pick Canberra because it's the first one on the list, and it's more real than the Cloud City of Bestman. So, right, there you go. The problem is, at this point, it's going to take a little while for this to load up. So I don't know if I'll edit this out or not, but you can see it's going to Australia. Isn't this cool? We're going halfway around the world just to, like, put a few graphs together, or a few models together. So, yeah, I might edit this out, or I might just show it to you so you see how long it takes, so you know what to expect when you're doing it yourself. So, in the meantime, I'm going to take a drink of water. Oh, look at that. It's done. Yeah, so having done that, we need to make sure R can access the commands that get used in that package. So you use the library command for that, and then you specify LME4 within the parentheses. And then this might take a little while, but no, it's done too. All right, so now we're ready to go. Didn't take that long at all, so I'm not going to edit that out. And hopefully you enjoyed the boringness of watching that. But now we're going to use the Elmer command, which I think I mentioned last time. So we're not using LM, which stands for linear model, or GLM, which stands for generalized linear model. And we're using Elmer instead. So the ME here is going to be mixed effects, right? Yeah, and then you can just call it Elmer, like a, some farmer from Iowa or something like that. But a mathematically sophisticated farmer from Iowa, I guess you could say. So anyways, as we get into this, if you're going to use the Elmer command, one thing you have to know is that you need to specify at least one random effect in the model for that command to work. Otherwise, it's going to be like, what are you doing? Why don't you just use one of these other options instead? They're easier to run. So try number one. Here's our first attempt. And I'll kind of write this out. You can already see the output there, but I'll show you how it works. And we'll make it like this maybe so you don't see that right away. So we're looking at F0 as our dependent measure. We're using this Elmer command. Average type. Whoops, I think I might have to go back and load this in. Sorry, I just realized I skipped the crucial part of everything we did before in the first lecture. So let me do that quickly. And then we'll walk through how to run the Elmer command. And I also created averaged height out of that. So that was just sort of the normalized height for our class. Okay, so done with that. And now we're going to go back to this command. And I'm glad I walked through it, but we're using the Elmer command. We're going to create a mixed effects model for F0 as it depends on this fixed effect of height, or averaged height in this case. And then we have random effects of speaker and word. Okay, so I'm just going to hit return. And this is what it spits out at me. I've got information here for both the random effects in this section and then also the fixed effects in this section. And I guess we can start out with the fixed effects. They kind of look like what we had at the tail end of the last lecture. So, right, I think our basic model gave us an intercept of 183.66. So we're pretty much in the same region there. And then the effective height was supposed to be negative 2.84. And we're at negative 2.88. So it's basically the same. But we have a little more information now about these random effects. So like I said, there's always going to be this residual variance that's left over that you can't totally explain and get rid of. So that's still there. Now we have some information about these two random effects of word and speaker. Yeah, so I've got those repeated here. And in this slide, I've also got this note that it looks a lot like the output for an ANOVA. because we have the variance, which you can think of as the sum of squares measure, and also the standard deviation, which is like the mean squares measure, listed for each factor. You might note there's a lot more variance being sucked up by the speaker effect here than we have getting sucked up by the word effect here, which, you know, hopefully kind of stands to reason. And if you kind of normalize those a bit, you see it's still much bigger in standard deviation for speaker than it is for word. But you know, that's kind of what you would expect. You'd expect kind of speakers to have more sort of individual variation in how they produce VOT than for like a word to change dramatically in VOT, even within a speaker from like one token to the next, right? So we don't actually say the P that much differently in Peel than we do for pool or something like that. But, you know, Susie could say Peel considerably differently from the way Bobby says Peel or something like that, right? Yeah, we can dig into that further. We'll actually look at our specific sort of values for this for each speaker as we eventually get to understand these models better. Right. So as I mentioned, with fixed effects, these estimates of slope and intercept are very close to our originals. But the standard errors and t-values are going to be different in this particular case. And one thing that's going on here is that there's still apparently a little bit uncertainty in how to interpret these models. So we're not going to get any F ratios or p-values out of this like we did in running just a regular linear regression model. So I'll go back to that as well. I think this is the basic model. Right, so what I was mentioning before, and I'll expand this a bit so you can see it hopefully. Right, so our averaged height, like standard error and t-value are now this. Or this is what they were for the basic linear regression model, and you can see that changes here in the mixed effects model. The t-value is considerably smaller. Even with a t-value of negative 2.06, you might expect that to be significant. We get a p-value listed with this t-value here in the basic linear regression model, but for the mixed effects model, we don't find out anything about that. And that's the point where there's some, or we don't get like a message about how to interpret it in terms of p-value. And that's because people are not, you know, totally certain yet about how to interpret it. I guess apparently the problem is that statisticians haven't figured out yet how to calculate the appropriate number of degrees of freedom for this analysis. So you can't just take this t-value, see how it fits on a t-distribution with a certain number of degrees of freedom and say, okay, there's your p-value. So you just kind of have to leave it as it is for now, but we'll get to p-values again soon enough. We don't necessarily have to, but I know they're reassuring because they give you an answer. So we'll find out how that's done with this approach here, just in a slide or two. Okay, let's try this again by including sex as a fixed effect. And you'll notice a few changes in the results. So we're going to just add this like we were adding factors to our multiple regression model the other day. So we have speaker sex and we have averaged height as our fixed effects. We have the same random effects down here. I'll hit return. And what do we get out of this? So again, I think it might be easiest to sort of interpret the fixed effects first. Before we go up here, our intercept was estimated to be 184.3 and change. Now we're getting a different intercept value of 209.1. So, right, that is sort of, again, using female as sort of the default value there. So rather than having kind of halfway between men and women intercept value for F0, we're getting one that you might get for like a specific average female. And then we're getting this effect of being male on top of that, and then an effect of average height. So, right, those look relatively familiar, but again, we don't know how to interpret those t-values. We can go back to the random effects, and we see the same three listed. One thing that's interesting here, though, is the amount of variance we're accounting for with both of these has gone down. So we had 1575 variance for the speakers. Now it's down to 508. And like without stating anything more authoritative than that, you could kind of say, well, maybe a lot of the speaker effect that we thought existed in the original was due or could be attributed more to the speaker's sex, right? So whether you're male or female determines a lot about how you individually like implement F0 or what F0 values you produce, but then there's still a bit of speaker variation on top of that, right? In terms of the word variance, that hasn't changed a whole lot here, just a minor difference between the two. But for speakers, we get a big change. So, right, as I said here, that means a lot of the unpredictability we were attributing to speakers before can be better explained by assuming it's part of the sex fixed effect. We also see that the intercept changed. The sex and the height slopes are also very similar to what they were before in the multiple regression model. I've mentioned these already, so I'm not going to dwell on them again here as I talk through this. What I want to get to, though, is whether or not our models are sort of significantly different from each other. And kind of the question you need to ask here is whether adding a factor will significantly improve the model's ability to predict F0 or to account for the observed values of F0 that we see in the data. Okay, so how do we do that? And the tutorial suggests using the following sequence of commands to evaluate the statistical significance of the model. And this is kind of interesting. It's a different way of doing this sort of hypothesis test than we've done before. But basically what we're going to do is create two models. So the first of these is I'm going to call the height model. So we'll have F0 as it depends on averaged height as a fixed effect. We'll have these two random effects, speaker and word, specify your data. And I don't think we've seen this REML bit before here, but that's just telling you that you need to spit out the output into a set of model parameters. Maybe I can move this up a bit so you can see it better. But I'm just going to hit return, and that creates the height model. And now we can see how that compares to the model with both height and sex as fixed effects in the model. And that's the only thing I'm changing is right here. And I'm going to call that the height sex model. Hit return. Nothing happens. How do we interpret this? We run, it's called an ANOVA in this command, but it's going to wind up being one of those analyses of deviance that we saw before. So it just says compare these two models to each other, height model and height sex model. And I'll hit return, and we'll see what happens. We get a lot of information. We'll get to the next slide here in a second. But it's basically saying the height model is kind of the more basic model here because it has a fewer number of parameters. So it's the one that's sort of, this is sort of testing the hypothesis against Occam's razor again. So it's saying like, well, we're going to add another parameter to this model, which is speaker sex, and is it worth it to do it? So we see like these numbers like the AIC, the Akaike information criterion, and also like how much does that change? And remember, smaller is better for that number. And then the Bayesian information criterion, also smaller is better. We don't need to worry too much about all of these guys, but we see again a measure of deviance and a measure of chi-squared, and that winds up being the one that we actually care about or that it gives us a p-value for. So it gives us a chi-squared measure, like just a number that fits on one of those chi-squared distributions when it has degrees of freedom of 1. This has a degree of freedom of 1 because that's the difference in the number of parameters here. And we're just seeing whether that one change in parameters will generate enough sort of improvement in how much variance we can account for to justify the inclusion of that parameter in the model. And eventually, the way that gets interpreted is by converting the amount of variance you can account for with that parameter into a chi-squared statistic, interpret it with this set number of degrees of freedom in terms of a p-value, and if it's less than 0.05, then basically the answer is yes. You're good to go. You should add this extra factor into the model because it will account for a lot of variance. And we kind of saw that intuitively at least, right? In terms of like how much our variance went down here in these random effect reports from like 1,500 something to 500 something. That looks like a pretty good chunk of change. Yeah, the residual and the words still stay the same. Okay, that's how you run that sort of test if you want to kind of build up a model from scratch. I'll mention something interesting. So let's say we try this the other way around and we build a sex model first, and I apologize for that terminology, but it seems to fit. Anyways, so let's compare just the sex model with the height sex model. And in this case, we're kind of like using this model as our default or our starting point. If adding height to that, does adding height to that actually help out or improve the predictiveness of the model significantly? And it turns out it doesn't. This is kind of interesting when you look at it. We're adding another parameter here for height. These information criteria are going in the wrong direction. They're actually becoming bigger when they're supposed to be becoming smaller. Anyways, we get a very small chi-squared value here, 0.16 and 1 degree of freedom. That has a large p-value associated with it. So if you had started out with the sex model, there's no need to add height on top of that. Basically, it doesn't help you in terms of accounting for the variance. Right. Actually, I'm kind of curious. I don't think I ran this command before, but we can look at kind of the variance we get by speaker if we remove this height feature here. We're playing around. Yeah, see, look. So our random effect variance is 451 with just sex as a predictive fixed effect here. So that's pretty small, right? And then if we were to go from that to the height sex model, we'd have a greater amount of variance being accounted for by speaker. So it kind of gets harder to predict if you have both of those factors in there. It's better to just stick with this, right? Okay, that's the idea. And one of the points I want to make on top of that is that the order in which you add factors makes a difference, just like it did for the multiple regression and logistic regression approaches. So like the amount of variance you're able to account for when you add a new factor into the model depends on how much you were starting with, basically. That's how these things get interpreted. I will mention as well that you can create sort of the null hypothesis model in this fashion. I was talking about this earlier, but instead of having sex or height as a fixed effect here, you can just have no fixed effects and just say, just start out with one. Just give me a model that has only the intercept in it. I'll create that model and then maybe I'll run it this way too. So this is going to have, no fixed effects, but it will have random effects. So like I said, you can run one of these models as long as they have some random effect in them, but I guess you don't need to have a fixed effect. And if we do that, we just get this report about the random effect, variance, and standard deviation. And so this is getting bigger, 2146 for the speaker variation. We get an intercept that looks like it's kind of halfway between the females and males again. But that's, what we're starting off with as a default. That's how much variance we need to kind of account for. The interesting thing, though, is that you can test the significance of adding each initial factor to it in this fashion. So how does the model that has only sex as a fixed effect compared to the null model? Well, we get a significant p-value here. We get a big chi-squared value as well. We could also look at, how does the height model do? And then we also get a significant effect here. So we could say, well, it's worth it to add either of these factors to our model. But the one that will give us the bigger payoff is adding the sex factor first, right? We get a bigger chi-squared value. You get a bigger reduction in AIC, that sort of thing, right? So, I've seen kind of two different approaches to this. One is where you start out with a null model and then you sort of add factors in in order of like how much variance they account for, or how big in this case the chi-squared value is. So you'd want to add this one first, and then you'd see, well, does it make sense to add the next factor on top of it? And in this case, we'd find out the answer is no. If we already have sex in the model, then we don't need to add height into it too. That doesn't give us an improvement. So in that case, the amount of variance you can account for height independent of sex doesn't help. The reason it looks like it's adding a lot of predictability in this model is because height is correlated with sex, right? So guys tend to be taller than women, and it's kind of misinterpreting the sex effect as a height effect for that reason, I guess you could say. So that's one approach I've seen, and it's kind of the approach that's implicit in this tutorial, where you start with the null model and then you only add factors to it if they significantly improve the predictability of the model until you run out of factors that you can add, basically. And so that's actually the way the homework 11 problem on this is structured. The other approach that I've seen that is much more common these days, and for reasons I don't entirely understand, but I'm just going to report it to you anyway so you know, but the other approach is to come up with, like, just throw everything in the model to begin with, and then just pick things out if they're not significant. So like if you remove something and it doesn't change the significance of how much variance you can predict in the model, then it wasn't doing anything anyway, so you leave it out. So you go from everything and then you winnow it down to just the stuff that actually helps, rather than starting from 0 and then building it up on top of that. Yeah, I really need to do more research on that and why people seem to prefer that approach. Apparently it's theoretically sound, but from my perspective, it looks like it would probably give you more a potential for more false alarms. But be that as it may, I just want to put it out there so you know that is often how it is done. Speaking of throwing everything but the kitchen sink into the model, I will let you know that you can test interactions for mixed effects by using the star operator again in R. So I'll show you just one example of how that works. We'll create an interaction model here where we have both of our fixed effects here, and then we're also going to look at the potential interaction between the two, because I said, they two have an effect on each other with the star operator right there. So we'll create that interaction model, and then we can test the interaction explicitly to see if it helps by comparing that model to the model where we're just adding in the factors separately. So this height sex model had the two by themselves like this, where we're just using the plus operator between them. So is it better to get that interaction in there? And it turns out the answer here is yes, which is interesting to me, speaking of potential false alarms. So this is a p-value that just slides in under the bar at 0.042. And that's for our data for this class. And it turns out this interaction was not a significant improvement for our two-factor model back in 2018. So maybe this matters, maybe it doesn't. But either way, that's what the results of the test show us. So actually, and I'm kind of curious, since we said we didn't really need to add height to the model anyways, we could compare those two. So the interaction model doesn't do better than the sex model on its own with just the one factor. So take that for whatever it's worth. And again, this is kind of instructive, I think, because you're adding two parameters to the model in that case, both height and its interaction with speaker sex. So there's a kind of heavy cost to pay there that needs to be justified by a significant improvement in predictability. And it's not quite there, evidently, because of this p-value. Okay, just give me a second. Right, so another command that's really useful, I think, in helping you understand what's going on in these models is that you can type in the coefficient command to see what is going on with the parameters in the model. So this is the model that has both height and sex in it as independent fixed effects. And what it does is it reports what effects these two factors have on both the random effects. Maybe now that I've done this, I think I might just go back to the model with only sex as a predictor, and we'll compare it to this one. So this one's a little bit simpler. And we'll start with speaker, because with speakers, we're accounting for a lot of variance. And this is basically saying, like, let's look at Charles. Maybe let's start with Karis. So Karis kind of has a default F0 of 232. And that's, before we were tweaking with the intercept of F0, when we had sex not as a factor, it wound up being something like 180 something. And when we had sex as a factor, it jumped up to like 210 or so, because that was the average value for like female speakers. So Karis is kind of on the high end for a female speaker in that respect, for her intercept or default F0 value. If she were male, what you would do is subtract 86 from that value consistently for her. So that would reduce it to something like 146, I think. Yeah, but she's not, so that just sort of remains the default value of F0 you use for Karis. Charles is male, so you get an intercept, or his specific random intercept is 208.79. But then he is male, so you subtract 86 from that, so you wind up with a sort of default value for Charles of 122 or thereabouts, which again is fairly typical average F0 for a male speaker. So you add this, or I guess effectively subtract this factor for the males in the database, but for the females you don't. But the kind of fun thing here is that you wind up with these random intercepts seeing like how male and female speakers kind of compare to each other on the same baseline. So, you know, irregardless of, well, I'll put it this way. So like Charles kind of winds up having an average F0 just as a speaker. Karis has a pretty high F0, and then you can normalize and say, well, even for a woman, she has a fairly high F0. And then you can go over like Duchan and say, well, he has a low F0. Like even for a guy, he has a pretty low F0. Actually, if you take Duchan, it's supposed to start out at 181, you subtract 86 from that, you get an average F0 of 95, which is pretty low because normally expect guys to have an average F0 of about 120. Like Lyndon is a dude with a high voice for a dude. And then Summer is a female with a relatively low voice for a female, but just also you can kind of cut this sex factor out of it entirely and just say, you know, this is a high voice and this is a low voice, adjusted or normalized by gender. Yeah, so you can kind of interpret it that way. And also we see a similar sort of setup for the random intercepts for words. So like, you know, these are the baseline sort of F0s you get for each word for whatever reason. So I'm just looking for highs and lows here. So Cole has a relatively high F0 by default. Pool has a relatively low F0 by default. And then you just say, well, if we have a speaker, you know, who's producing this, we'd expect F0 to start at 204. And then if it's a male speaker, you subtract 86 from that. So Cole being produced by a male would wind up being like 118 or something. Yeah, and then for, yeah, I have Cole and Cole. I don't know if that's really what I wanted to do. Yeah, probably not. Anyways, be that as it may, you see kind of less, it looks like, at least on the surface, and we know, having run the model too, that there's less variation accounted for by the words. These aren't differing from each other quite as much as we see in the speakers, right? So like 232 versus 181 is a fairly healthy difference. The biggest difference we get here, I think Teal is the highest and then Pool's the lowest, so it's within that range, right? Going back up here with the height and sex model, same sort of thing, right? So the intercepts get tweaked a little bit because, you know, now we're taking their height into account for each speaker, but they're basically the same. So Duchan was at 181 before, Karis at 232, Charles at 208, now at 205, 234, 183. So, you know, same general region. So in this case, you'd say, well, Karis starts at 234. You don't incorporate this factor because she's not a male speaker, but then for each centimeter that Karis is tall, you incorporate this factor, and I can't remember how tall Karis is, but, you know, like 160 something maybe. So 160 times this factor, you'd incorporate that into her average F0, more or less. Yeah, so this would apply to everybody. And again, take into consideration we're adding these factors independently, so you don't sort of consider any sort of interaction between these two numbers. You just apply them independently, and then that's the sort of average F0 you get for a speaker. Yeah, so that's what the model coefficients look like. I think they're often quite useful because it gives you a sense of how these, you know, this individual variation that the model is accounting for. Yeah, so I walk you through that here. Like gave you the example, Lyndon's intercept value would be reduced by 82.4 due to the fact that he's male. That's the model up here. And then you also account for his height on top of that. Okay, whether or not, oops, wanted to fix that, oh well. Whether or not they apply, the model assumes that the effects of sex and height are the same for everybody. That's the random intercept model. So you just apply them across the board, as I mentioned before, but it's also possible to construct a random slope model whereby each speaker and or word may have different slopes for the otherwise fixed effect of height on F0. Yeah, so I'll show you how one of those works as well. But what we're going to see in this case is not only like speaker-specific intercepts, but also speaker-specific effects of these other factors too. That's the idea. The problem is in this particular case, it's hard to kind of gauge that with this data set because the speakers can't change their sex or their height for this study. So I'm going to go back to the VOT data we originally collected back at the start of the semester and show you how this might work for different factors on VOT. So we'll read that in and then create a couple of models just to show us that stop place of articulation has an effect on VOT. Sorry, I do have a cold. So our null model is using VOT as the dependent measure. Maybe we'll move this up a bit. And then this is a null model, so we have no fixed effects. We do have the speaker and word as random effects. We'll just create that. And then also create what I'm calling a stop model. So this has stop as a fixed effect in comparison to the null model. We can compare the efficacy of adding that parameter to the model, see if it's worth it. And lo and behold, it is. Yay. Stops are actually accounting for the VOT measures we get in this case. And we're doing this even though we're adding two parameters to the model here because there are three different places of articulation. So our degrees of freedom wind up being 2, 3 minus 1. Anyways, be that as it may, I'm going to expand this with a random slope model. I'll put it in here. So this is kind of the first step of doing this. So everything looks the same between these two. Except in this random effect, which used to be just one line speaker, now I have 1 plus stop speaker. So in theory, I could add this to the word here as well, but I'm not going to. I'll just explain what this is saying is that that effect of stop, maybe I'll go back, that effect of stop could be tuned to each individual speaker, right? So like in this model that only has stop as a fixed effect and doesn't have random slopes, like Andrea's sort of default VOT is 69.2 something. For P, you subtract -17 from that, so it winds up being like 52. For T, you subtract about 6.8 from that, and it winds up being like 63 or something. So P is going to have the lowest VOT, T is going to have a slightly higher VOT, and then K, which is first in the alphabet, has sort of the highest as the default or intercept value for VOT. And that's going to be the same across the board for every single one of these speakers. We're just kind of adjusting like where our default our VOT is. So like Chemon has a really high VOT. I guess Andrea has the lowest one. Maybe that's an influence of Spanish. I don't know. Anyways, so what we're going to do with creating this random slope model is we're going to say, well, these values for the effects of the individual stop places could be tuned to each individual speaker. So we can get different values in these columns, in a column like this, or different values in a column like that. It doesn't make a whole lot of sense to add that onto as a random slope factor to word because like the words are just stuck with particular places of articulation at the beginning of each word. So, we're not going to add that random slope factor to words. We're going to add it to just the speakers, and we're going to see what we come up with. We'll do two things on top of that. So, we'll hit return. Now we have the stop slope model. And actually, maybe the first thing we can do is to confirm that this is an improvement on what we saw before. And it is. We're including a lot of different degrees of freedom now, but we're still getting a big bang for our buck. So yeah, including those random slopes helps, it turns out, which is nice to know. Now we can kind of look at the coefficients as well and see what they're telling us. And this is kind of what I was alluding to before, right? So let's go to Andrea's numbers again. She started out with 69.2, etc. Now her default is 78.69, so on and so forth. And then you subtract 27 from that for the P, so that would give you around 51 or so, and then 25 for T, so 53. So her P's and her T's are pretty close, and then the K's are considerably higher. You can get different effects. So I talked about Chamon. So Chamon starts out with a default 134. You subtract 13 from that for P's, and you add 5 for T's. So actually his TVOT is a little bit longer than his KVOT. So that sort of random variation can get into the model as well. It doesn't have to be a consistent effect of place of articulation for every single speaker. So isn't that cool? I think I'm going to want to run these and take a look at that residual variance again. Just to, let's see. Sorry, I'm doing this on the fly. I should have planned ahead. Just go back to our original commands, which are up here somewhere. This one. I just want to take a brief look at that. Variance. Stop. Apologies for doing this on the fly. So this is when we just have the stop as a predictor as a fixed effect, and we don't have random slopes. Just to see what this looks like. So in this model, we're accounting for this amount of variance by speaker only. And then we have 261 in residual variance. Let's see what happens if we just add that to the speaker as a random slope. Oh, this is interesting. So it's kind of coming up with like how much variance so we start out with 741 here, and then it shows you how much variance you can kind of account for with these random slopes for P and T. So this is kind of like the benefit you get overall. I guess you would say. It also shows some correlations between these factors, which is kind of interesting. So this is what we're benefiting from in adding that random slope factor. Just to kind of make it numerical, I guess, for you. Okay, where was I? Right, we did that, and we looked at the coefficients as well. And I'll just wrap up with the punchline for this part and just say again, in the more sophisticated model with random slopes, there are speaker-specific effects of each stop of place of articulation on VOT. So that's what you can get out of that. All right, so it looks like there's benefit to adding that feature to your model, and that's what Bodo says in the tutorial as well. So he says, include all random slopes that are justified by your experimental design, and do this for all fixed effects that are important for the overall interpretation of your study. So in this case, our basic question would be, does stop place of articulation have an effect on VOT? So that's part of the primary research question, even though it's not super exciting, but because of that, we want to be able to include those random slopes for stop place of articulation into the model, just so we know, like, if it's having this effect by individual speakers, we need to kind of separate that individual speaker effect out from like the fixed effect that applies across the board. And yeah, so in his example data set, he cared about politeness as an influence on F0, but didn't care so much about the effect on sex on F0, which we knew about already. So he specified for that reason random slopes for politeness, but not for speaker sex. So he's just focusing on the one that mattered to his research question again. And that was a toy research question anyways, because it was part of that tutorial, but still, it's a valid one. It's interesting to think about. So anyways, note that the amount of underlying variation in your data can limit the number of effects you can specify in your model. And we didn't talk about this, but if you remember, when we created that VOT data set, I had you guys repeat each word 3 times, kind of so that we could start doing these sort of repeated measures analysis at the end of the semester on that data. So it all comes full circle, planning ahead. Anyways, just give you an example of where that comes into play. It's not possible to produce a model with random slopes and random intercepts for both the stop and vowel factors in our data set, because we don't have enough repetitions to kind of play around with that. So I'm just going to kind of create an overloaded model here with both stop and vowel as fixed effects. And then there are also random slopes for those factors as well by word and by speaker. And if I hit return here, it's going to think for a while and then eventually say, I can't do this. I can't figure this out, so try something else, please. So, right, in this case, you'd probably need more than just 3 repetitions of each word per subject to get that model to work. So watch out for that. You might run into this problem when you do, if you apply this to your own research results, and just, that's kind of where it's coming from. Yeah, so like the tutorial says, like, include everything you can that, because these are useful, but to a certain extent, it may help you actually run the model if you're a bit parsimonious with how you apply that approach. Also, a couple of notes on when to designate a factor as fixed versus random. So the tutorial says a random effect is generally something that can be expected to have a non-systematic, idiosyncratic, unpredictable, or random influence on your data. So just like you got one random person off the street or from the 201 class, and you brought them into your study, and you don't know exactly what they're going to do. So in experiments, that includes subject and item, usually, and you generally want to generalize over the idiosyncrasies of individual subjects and items. So normally when you're running a study, you don't care specifically about how Bobby produces VOT or F0, or you don't care so much about what the specific VOT is in a word like coal. You want to have something more generalizable to try to figure out, like, what is the effect of stop, place of articulation, or height, or something like that, right? So fixed effects are those things you normally care about more profoundly. They're expected to have a systematic and predictable influence on your data, and you're trying to capture that sort of predictability by running the model. So another way you might think about this is that fixed effects are repeatable. So like if you ran the experiment another time, you could test those same effects again, like just have everybody produce P's, T's, and K's in the same way. But you wouldn't necessarily run the study with the same subjects, right? Because again, you're not caring about how does this particular set of speakers produce this, or I don't need to know exactly how Susie does it. I just want to know like whether this external factor of like place of articulation has an effect on VOT. So yeah, you kind of would wind up sampling the same levels of place of articulation when you do that, but you wouldn't necessarily sample the same individual subjects to run the experiment again. The value in understanding the fixed effect is that it could apply to like a different set of speakers. And that's actually kind of why I like running these experiments, these mini data collection experiments for this class with a different group of speakers every single time. They usually work out pretty much the same way, but not always. That's why we're here. So Bodo also points out that fixed effects are supposed to exhaust the population of interest. So like male and female levels for sex and gender, or if you prefer, then you could also throw in like a non-binary category there as well. But that's kind of the idea, is like everybody in the group will be one or the other of these levels for this particular factor. Random effects, on the other hand, generally sample from the population of interest. So you might include various levels from a language in your study, but you're not likely to include all words from a language in your study. I think I would put that a different way. You might include a specific set of words from a language in your study, but not all of them, because you don't need to include all of them, right? That's also one of the reasons why we're here, is we can kind of save some time by learning how to extrapolate from the specific experiences or data we collect in life. Or for that matter, all speakers of a language. You don't have to interview all speakers of English to find out something about how English works, thankfully. So for this reason, normally linguists make things like words and subjects random effects in their model, or any particular item as a random effect in your model. And by item, I mean this item of data in my experiment. Yeah, and I think that's pretty much all I have to say about this for now. So I'm going to sign off. This will be a topic in homework number 11, so I still need to make a video about that and post the homework to the website. But for now, for this semester, we've covered as much as we need to cover and can cover, I think, because these are bonus lectures. So I hope you appreciated them, and I hope you appreciated all the lectures altogether. It was fun making them in another strange semester at the University of Calgary. All right, I'll see you all somewhere down the road.